Good morning, everyone. My name is Rodrigo. We are going to start the event with our first mini course given by Professor Paulo Rufino. He's going to talk about stochastic calculus. I think you have to use the microphone, otherwise it won't appear in the recording.
Then I have to keep it in my hand. Right.
Sorry.
Okay. They are recording, so we have to use the microphone. So this is a mini course on stochastic calculus, which for some of you may be already well known, or part of it is already well known, but maybe not for all. And the sketch of this mini course is the following. On the first lecture today, I expected to make some preliminaries. And Brownian motion. It is the second lecture, or maybe talk, which is going to be very condensed. I'm going to talk about properties of martingales. The third talk on stochastic integration and Ito formula. Stochastic integration, Ito, and Stratonovich. And Ito formula. Of course, in applications. And I want to finish with stochastic differential equations. Some comments or idea of the proof on existence and uniqueness of solution. Some idea on flow generated by stochastic differential equation. And well, from here on is somehow more related to stochastic dynamics. Dynamics. And depending on how fast or how slow we do this, I can introduce some geometry here. How this technology, how this stochastic process fits in the geometrical context. Just recall that we have, so somehow it's more or less divided like that. It's not precisely. Maybe if I have depending on the first lecture today, I may introduce at least the definition or some P variation, which is going to be critical for martingales and is related to the course in the afternoon on Routh path. So I may put one step here in the first lecture. What else? We have two exercise lectures. Which is going to be with Lorival, which is a PhD student of us here in our group. Lorival, which is over there. Thank you, Lorival. And he's somehow also in charge to not only questions or comments on stochastic calculus, but also on the map of the campus, on the restaurant, and many other informations. Right. Thank you. So let's start with some preliminaries. So what I am assuming here is not much, but on basic probability. A measure theory and some probability. And we start with some. So essentially here in the first lecture, I'm just going to introduce notations, and maybe if I have time, one proof, but mainly is a description, mainly is notational. So not a proof. So don't be disappointed. I am going to make sketches of proofs from the second lecture on. Okay. For our notation, we always consider omega as a probability space. A probability space which we consider is complete, which essentially means that if a set has full measure, then any set which is bigger than this is also measurable. Or this is equivalent of saying that if a set has measure 0, any subset of 0 measure is also measurable. Okay. So I don't need to make a definition. This is a sigma algebra. P is subadditive, etc. From F 0T sigma additive on disjoint sets, and all the definitions, which I am assuming that it's known. Expectation, a random variable x from omega to a metric space. Metric space with Borelian. If it is measurable, this is by definition a random variable. This metric space most of time is a Euclidean space, or it is a manifold, or it is a Lie group. Take your favorite state space. This is what we call a state space. State space of our stochastic process. Lie groups, matrices, etc. Etc. And All right. Expectation of x in omega if exists. If it exists. Which we are going to assume in most of time that it is integrable, that's in L1. And if x is in R, this is x dx star p integrated on R. This is again just a notation that x is the push forward of the measure p of A equals probability x minus 1 of A for all A in the Borelian of the state space. Right. Just notations. What else? A typical exercise, which I imagine most of you have already done at this point of a preliminaries on probability, is to prove that a Gaussian in Rn x star p 1 x in Rn 2 pi n over 2 square root of determinant of the covariant matrix exponential y minus m c x minus m x minus m over 2 dx. That this is a probability measure on Rn. So C is the covariant matrix. Covariant matrix. Cij is the expectation. Xi minus the average, or the expectation of xi, xj minus expectation of xj. C is positive definite. If not, it's a degenerate Gaussian. This is typical notation for this is a normal average M and matrix of covariance C. This is C to minus 1. Standard and a well-known result. Conditional expectation. So one of the exercises to prove that the measure the measure on Rn. This is the probability. Conditional expectation is a filtration with respect to sigma algebra or sigma fields, as you prefer. So if we have G, a sub-sigma algebra, and we have X integrable with respect to omega F, I mean X is F measurable with image in R. Then the conditional expectation of random variable X with respect to a sub-sigma algebra is the best approximation which one can get of random variables which are G measurable. So in this sense, I said it's a filtration. So the notation, conditional expectation of X with respect to G. Let me denote here by X tilde, just to make notation easier. Then by definition is that integral for any G in the sub-sigma field G of X tilde with respect to the probability P, or P restricted to G if you prefer, is not critical, it doesn't matter. But you may like to include this. This equals the average of X in the same set G, but when we integrate with respect to the measure P in the full sigma algebra F. So in this sense is the best approximation for something which you don't have access to the measure of all sets here. But the question is how close we can get to this random variable, right? For example, if G equals the trivial sigma algebra, X and omega, then the best approximation is the expectation of X. Okay? It means there is no approximation. This is, you are completely blinded with respect to X. The best approximation is X is the average of X itself. Right. Properties. So it's a linear continuous positive operator which goes from integrable random variables F measurable, and R goes to L1 omega G R. It's a projection in the sense that if X is already G measurable, then the conditional expectation is itself. So this is almost truly, and the existence is guaranteed by the Radon-Nikodym theorem, which of course doesn't care doesn't care about sets of measure 0. Okay, in particular, there is this projection, right here, projection. In particular, in L2, it is orthogonal. I will, if you don't mind, I will abbreviate like that. So L2 is a Hilbert space, and we have orthogonal projection. If here we have L2 of f of g, I will meet omega of g going to R, and all the ambient is L2 of f R. This is x tilde. In this sense, is orthogonal. The difference between x tilde, and is this vector is orthogonal to L2 of G. Again, a standard exercise to be proved. Right. What else? Existence. I am going to use quite soon that if the sigma algebras are independent, then the conditional expectation is constant almost truly, given by the expectation itself. Here. So another property is if the sigma algebra generated by X is independent of G, conditional expectation of X, G, well, I sequence this property and I carry on, and I hope I'm not going too fast or too slowly for taking the average of the audience. I think is somehow is okay. Or right. So let's put things to move. I mean, let's put some dynamics on here, which corresponds to consider stochastic processes. Is a family of random variables, which I think most of you, stochastic processes is a measurable x, which goes from omega t to a state space. So state space, which for us most of the time is going to be R or an Euclidean space, or R n. This T can be discrete, can be a group, semi-group, and most of the time for us is going to be positive real, and where we are going to construct the Brownian motion. So you all have a good understanding of this, and if we fix omega, then x of omega is a trajectory. We call this a fixed trajectory. And the other way to see this is to fix t, xt dot. This is a random variable. Well, Brownian motion. The special or our favorite stochastic process, or at least for beginners, after we find many others which are also, if not equally interesting, but this is the basic one, which is, yeah, it's not bad word to say that it's one of our favorite. Any other process we compare, or we want to compare properties with Brownian motion. So Brownian motion, which I should put in plural, Brownian motions, infinite number of them. And the definition, it is a process, stochastic process, I mean measurable, etc. B with time starting at 0, based on a complete probability space, going to R. So initially, to fix ideas, I am going to consider real line R1, but we can easily extend it to Rn. Just take independent versions on each coordinate, right? But I'm going to fix ideas in R1. T omega. So what we expect to this process is the Gaussian process, in the sense that fixed t, we always have Gaussian random variables. Increments is also random variables, is also Gaussian. And we expect continuous trajectories. Fix omega, then trajectory is continuous. And one can think that we are going to be too demanding. So we start at 0. So this 0 at time 0 equals 0, almost surely. T bt omega is continuous, almost surely. Independent and Gaussian increments. Say, start with stationary. Gaussian increments, in the sense that for s less than or equal t, b t minus bs is a Gaussian measure, normal with average 0 and covariance t minus s. And thirdly, we have independent increments if the intersection of the increments is empty. In the following sense. the following sense: for 0, T1, T2, T3, and T4, we have BT4 minus BT3. By this symbol, I mean independent. The sigma algebra generated by this is independent on the sigma algebra generated by T2 minus BT1. Then for disjoint intervals, they are independent. Right, very nice. So the idea one has of a Brownian motion on R, or even on a Euclidean space, is that we have trajectories starting at 0, and they are spreading out there. So if we fix T, and we draw in 3 dimensions the density of the random variable at time t, the density is something like that. Then the probability that the Brownian motion cross this interval A, say, is easy to calculate. The probability that trajectory pass through here at time t is calculated using the Gaussian distribution. And if we take an extra T1 and take another one T2 and select another set A1 and A2, we can again calculate the probability that the trajectory pass through A1 and A2 simultaneously. I mean, not simultaneously, I mean the same trajectory cross both. One not simultaneously, one at time T1 and the other one at time T2. So if the trajectory is here, then from here to there is a Gaussian centered here, another Gaussian centered here, with covariance proportional, proportional to the time. So it's a diffusion which is spreading on R. Okay. So average is always 0, but we can see that the variance expectation of B to T equals T. So it's spreading infinitely and without any boundedness. So normally we fix it. Normally we take for martingales or the stochastic process. If necessary, we fix the process up to a time t, capital T. But not yet. Not yet. And just giving the definition. And the problem is existence. Does it exist? We can be very demanding on establishing a process. Say that they are Gaussian and independent at each time t. Is it possible? Yeah, why not? You understand what I mean? We want a process, and engineers and physicists. I'm sorry, I forgot the microphone, but I hope it's not too bad. So engineering and physicists would love to have a process which are independent at each time T1 and T2, that is Gaussian here and Gaussian here, and they are independent at time T1 and time T2, and are continuous. This is the dream of engineers and physicists, but it doesn't exist. So it's we can increase the list here and put a very nice properties and claim that well, a 4 that is that trajectories are C infinity, and well, you can dream about all of this, but it doesn't exist. Okay, so this is why it is the next half an hour I'm going to point to the main results which prove that it does exist as a Markov process. So we are stating that it's a Markov process when we have this independence. So the future does not depend on the present. So the main step on constructing Brownian motion another remark is that is a special kind of a Levy process, which many of you is already familiar with the Levy process. Levy process are specifically stationary increments and independence, starting at 0 and continuous in probability. So Brownian motion is a particular case of Levy process, which again is a martingale but with jumps. It's a fantastic new tools for stochastic analysts or stochastic dynamicists. How to deal with jumps in the process, or jumps with on stochastic differential equations is also a very rich area of research. But it's not the topic on this mini course. Just taking the chance to open your eyes for some more general stochastic processes. Right. So as a Markov process, back to Brownian motion. As a Markov process, we have the following transition probability. We have the following transition probability, that the probability, well, it's going to be homogeneous on time, but if you prefer, we introduce 0 here. The probability that at point X we jump to set A is given by square root 2 pi t is a Gaussian. So as I said before, we easily calculate average is X. So y minus x, inner product here, which corresponds to the square t dy. So these are the transition probabilities. And the construction passed through the following. So P, the family P, T, X, A, establish so this family establish a family of probabilities in finite dimensional cylinders of trajectories, and from there we are getting the existence of a process which satisfies the probabilistic conditions, not yet the analytical condition, which is continuity, but the probabilistic condition is satisfied. This is the Komogorov extension theorem. So it's based on this, establish a probability probability on the algebra or field. I am of finite dimensional cylinders. In the following sense. As I give the intuition here. So if you have a sequence, a finite sequence T1 up to Tn, and a finite number of Borel sets A1 up to An, then we can calculate the probability that one cross the other. Probability, ups, given 0, T1, T2, Tn, and Borelians of the real line. We have probability that BTI belongs to AI this is calculated A1 integral up to AN probability that X n minus 1 goes to n minus 1 here. I am reconstructing that formula what I meant here. That to go from here, which I'm calling x1, from here to there, and from here to the third one, and from to the fourth one, and so on, to write precisely what is this probability. I am anticipating, it's in some sense the proof of the Komogorov extension theorem, which says that if there exists an algebra, probability on the algebra, which is sigma finite, and it's a probability, then there exists a probability in the sigma algebra generated by these cylinders, and there exists a probability space where we can define the process. Okay, so in some sense, this is the proof of, or idea of the proof of Komogorov extension theorem, which I'm going to state in 5 minutes. So this is the last variable jumping to an, integrated with respect to p x n minus 2, jumping to dx n minus 1, etc., up to probability to jump ups subindexes p t n minus t n minus 1. As I said, it is homogeneous, so it depends only on the difference. Okay? Here, t n minus 1 minus t n minus 2 of the previous one of the x n minus 1 of x n minus 2 jumping to dx1. up to 0 to T1, 0 dx1. I mean, we are integrating backwards. So we look at the last one. If this is an, this is xn minus 1. We are jumping from xn minus 1 to an. This is the last function. We are integrating this function, changing xn minus 1. So we are changing xn minus 1 here. For each of them, we have a different probability, and we are integrating this. This is not gx1, but gxn minus 1. Sorry. Is it okay? Yeah. It's a chain of probabilities. Right. It is consistent or compatible in the sense that if one of them, it is compatible in the sense that if one of these A's equals R, then we can reduce the cylinder to a smaller dimension. Another name for this is Chapman-Komogorov condition. Chapman-Komogorov condition, which says that if we go 0 t x to a, it is independent. It is independent on the way integrated with respect to p s minus t minus s y a. So this is the function which we are integrating with respect to y, which is running over r. It's equivalent of being a Markov process. It means it doesn't matter if you pass. It doesn't matter if you have a trajectory from 0 and you at time t you want to reach a set A. It doesn't matter where you pass in the between. If it is down here, up there, it doesn't matter. When we integrate with respect to, this is S, when we integrate with respect to all possibilities, it's the same probability if you go straight forward from X to A at time T. Okay? Right, and this is, I present now the probabilistic theorem which guarantees the probabilistic properties of Brownian motion, which is theorem Komogorov extension, which says that if we have a family of transition probabilities, if Pt is a family of probability transitions satisfying Chapman-Komogorov chat from Komogorov. It implies that there exists a probability space state space to the power r greater than 0. It means all possible functions from positive r to state space, which in our case is r itself. With the sigma algebra generated by cylinders, cylinder is set like this, as I said before, finite dimensional, and this is a sigma algebra generated by them, which in fact coincides with when we prove that Brownian motion is continuous. It coincides with the sigma algebra generated by the uniform norm on the space of continuous functions. I'm not going to prove. With a certain probability p, such that the canonical process is take the trajectories it's an interesting way that probability space here is again space of trajectories. So we easily can define trajectories out of that. Just take an element here, just take an omega here, which in our case equals r, right? Just take an element here. An element here is a function, which is in this sigma algebra, and the function is omega t. Then this is such that this is a Markov process. With the prescribed transition probability. Prescribed. Probability transition. Is it clear what the meaning of this? That not only proves that there exists the Markov process, but it gives explicitly the probability space where this process is constructed. The probability space in the sigma algebra. This is not much more than, together with what we have written before, is not much more than the Karateodori theorem on extension of pre-measures on algebra extending to sigma algebras. It's not much more than that. Okay. So in this sense, I mean that the probabilistic aspects of the Brownian motion is satisfied as a Markov process in Gaussian. So the problem here, the problem now is to prove the existence as a continuous trajectory, right? And before I show how to solve this, I am describe in which sense so we are going to take a process like this, which we absolutely have no claim, no idea, no glance of what is of continuity or any regularity of trajectory, and we have to make a modification of this process or a version of this process or something which has to be very precise. What sort of modification which we are allowed to do? And with a modification, we can reconstruct a continuous process, right? So before I state again the Komogorov theorem on the existence of a continuous modification which fits there, I'm going to explain what I mean by a modification. Okay? So we are going in the direction of continuity. But with a window here on the meaning of modifications. Modification or version or indistinguishability, which are just three ways to compare stochastic processes. Well, much more than that. I mean, the basic ones for a course on stochastic calculus on this level. So first, if we have a stochastic process xt defined on omega, say going to R or going to any state space, and we have another process defined in another probability space, we say that x and y are version of each other if they have the same law. If they have the same law, I mean the probability that xti belongs to ai equals, this is probability P, and here we have probability P prime. P prime. The probability that this happen equals the probability P prime xti pass through ai. Ti, as before, are subsets, finite subsets on the time, and ai are measurable Borelian sets in the state space. So the point here is that they can be defined in distinct probability space. So the second concept, the second comparison we make, which is the most relevant here for us, is the modification of each other. And in this case, we need the two processes defined in the same probability space. So x and y defined in the same probability space. Of each other. if for all t, I didn't state the time, but it's any other time t, then the probability that xt equals yt equals 1. And finally, they are indistinguishable from each other if they coincide along the whole trajectories. Modification is going to be relevant to understand what we are going to do with Komogorov extension. We are taking a modification. The third one, indistinguishability, X, is going to be relevant when we are going to prove the uniqueness of solution of stochastic differential equation. They are unique up to indistinguishability. X and Y are indistinguishable. One of the longest words in English, I know. Not in German, right? German has much longer. X and Y are indistinguishable from each other. If probability that xt equals y of t for all t, and the time, well, in our case is r greater than 0, but this probability equals 1. So all t goes inside the prescribed condition to calculate the probability. And of course, if they are indistinguishable, it implies that they are modification. If they are modification, it implies that they are version of each other. But version of each other is much somehow less rigid and more say interesting. They can be defined as I said, in distinct probability space, which is fantastic. And 2 and 3 are very restrictive. 3 is even more, which makes uniqueness of solution of stochastic differential equation even more interesting. So we close the window on this comparison, and now we go to Komogorov criterion to say, which gives sufficient conditions of existence of continuous modification of stochastic processes. And Brownian motion will satisfy this condition, and then we are done. And there exists, finally we can say there exists Brownian motion. And this is the theorem, which is known in the literature as Komogorov criterion. If there exists alpha, beta, k, 3 positive parameters such that expectation of x t plus h minus x of t, I mean, it is studying the increment. This to the power alpha if this is less than or equal k, h to the power 1 plus beta, for all t, and the time, I am fixing positive real numbers, for all positive h, then there exists a modification. There exists a modification x, say x tilde of x which is gamma less than beta over alpha, which is gamma Holder continuous. Good. Well, what does it have to do with Brownian motion? Well, first of all, let's just understand what is the condition. What's the criterion? The criterion says that that the increments are 1 plus beta over alpha Holder in L1. That's the interpretation of the condition. So if it is 1 plus beta over alpha Holder continuous in L1, then the trajectory is going to be gamma Holder continuous. There exists a modification which makes the trajectories gamma Holder continuous. Okay. So, and what about why Brownian motion fits well here? Does exist k? Does exist alpha, beta, k, which are positive, which fits to Brownian motion? The proof is based on dyadics. So essentially, with the hypothesis which we have, Brownian motion is always continuous when restricted to the dyadics, which is dense in the line. But we want more than that. We want continuity on the whole line. So essentially, is the proof is to fill the gaps, to fill the complementary of the dyadics in the real line. It's a beautiful proof, but well, somehow long is not the case to do here. But it's and well, what Brownian motion has to do with it? Well, it's we have that the increments. We have that the increments is Gaussian. Then BT plus H minus BT well, if we have power 2, then it is equals to T, which is the variance. Doesn't help, does it? No, it doesn't. We need a higher exponent on T. We need 1 plus beta. So it doesn't help. 2. For Gaussian measure, we know that odd powers is always 0. Uh, well, it's which would be good enough. But I was aiming at power 4, which for Gaussian variables is this 3h square, and then from here we get k equals 3, we get beta equals 1, and alpha equals 4, and from here we have that direct system modification. Direct system modification, which is for any gamma less than 1/4. But we can do it better, somehow better, and people do. So this criterion states we are, well, I am already convinced that we have a holder for 1/4, which is good enough to get a continuous modification. And but we can do better than this. We can reach in it's a classical result that Brownian motion can be alpha holder for any alpha smaller than half, which is not what we get here. But I'm not going to the details. I'm happy that I show you how to get at least one modification which is continuous. I don't want to go into the precise gamma equals half holder. So in some sense we have why not use 3? I'm not going to answer. Think about it. I wrote wrongly. It's the power without norm. So the odd powers 3 equals 0, not with the norm. Okay. So with this argument, with Komogorov criterion, the way I am presenting, we have to use 4, and the best we can get is this. So we have good and bad news here, somehow, right? Good news is It is there exists Brownian motion as continuous process, and bad news. Low regularity. It means that is not very well suitable for integration. So when if you want to integrate one function with respect to the other, in the classical theory, Stieltjes integral or Young integral, which is the topic also of the mini course today in the afternoon. For the Young integral, we need that f being alpha holder, and g beta holder, such that alpha plus b is greater than or equal 1, probably strictly greater than 1. And Brownian motion is too low. Regularity of Brownian motion is very bad. It means that integral of Brownian motion with respect to itself is not quite well defined if we look at trajectory by trajectory. That's why Ito introduced the stochastic integration to carry on with this problem that it does not exist as an ordinary integration, as a Stieltjes integration. It has to be interpreted in another sense. The convergence here is going to happen in probability, not trajectory by trajectory. Okay? It's just interpretation of what we have done. Right. Let me talk a little bit of the canonical process. And here we finish here with this Komogorov criterion. We finish the construction of Brownian motion. Let me talk a little bit on the canonical process, on the Wiener space. Wiener space is the space of trajectories of Brownian motion with the probability, with the corresponding probability. It's going to play a role when we talk about stochastic flows. We will need a shift on the probability space, and the shift corresponds to update trajectories. But I explain what I mean by updating trajectories. Just pull back trajectories starting at 0, making them starting at 0. So canonical process. If we take B, Brownian motion, from here on, I mean a continuous process, always. Or one version of the Brownian motion among the uncountable versions of them. I take one. And and to simplify, since there exists one probability space, I can construct it in any other probability space, which is somehow isomorphic, which is isomorphism of probability space is absolutely rich. And take one, and then I'm putting back omega going to trajectories, going to C0 functions f from R to R, continuous and starting at 0. This is defined almost truly. I mean, ignore trajectories which are not continuous. Okay? Then the Wiener space. W equals C0 with the probability P equals the induced probability. Oops. This is P. This P W is the induced probability of Brownian motion in the space of trajectories. I'm just restating things, but in the right space of trajectories, in the space of continuous trajectories. And W Borelians of C00 with PW is the Wiener space. And Brownian motion can be defined from omega. Again, for each omega is just, it points the coordinate t. If we call t a coordinate in this infinite dimensional space, it is just pointing omega of t. And this is again a Brownian motion. It's called the canonical process. And shift here, a shift by t, which is going to be relevant when we talk about flow, is to take an omega of s equals omega t plus s minus omega t. It means take any trajectory, cut it out, cut out what happens up to time t, consider what is in there, and put it back here. So this is I'm trying to copy the orange line, the orange graphic. I copy the orange graphic in the starting at 0. This is the shift. It plays an important role in terms of control, control theory. It means in a stochastic equation. So ignore everything which happens up to time t. So all the control which has been done in the equation up to time t, ignore and consider the future starting at t. The future starting at t in the same space means perform the shift. But we come back to this in the future. We have time to introduce some martingales, if you don't mind, especially p variation, which has somehow a motivation also in the course in the afternoon. If it's okay for you. So martingales. So let Ft contained in F a family of sub-sigma fields, sub-sigma algebra. A family increasing. An increasing family of, again, for complete with respect to the probability measure, family of complete for technical reasons, again, a family of complete sub-sigma algebra. Sub-sigma algebra. And let xt be a stochastic process which is adapted. By adapted, we mean that the sigma algebra, which makes xt measurable, is ft. Is it ft or is contained in ft? Is ft up to sets of measure 0? Well, they are xc is ft measurable. This is a sufficient condition, but it's probably is also sufficient. Adapted process, integrable. Which again is can be a bit too much. If we can weaken this hypothesis, we can ask that the positive part is integrable. But I don't want to go into this detail, so let's assume that it's integrable just to fix the main ideas here. And xt is an ft martingale. So to be a martingale depends on the filtration. Is an ft martingale if conditional expectation, if the filtration of xt with respect to f of s for s smaller than or equal t, this equals x of s almost truly, as usual. So the best approximation for the future is what happens in the past. And I make an example, our favorite process. Which else? And tomorrow I show, well, if we have one, we have an enormous family of martingales. And Ito integral is a generator of martingales. And but before we carry on, just one example. BT, Brownian motion. And we have to check. Well, it is integrable for each fixed t. And we have to prove that conditional expectation of BT given BS equals BS. As I said, this is probably the only proof, in some sense, the only proof I'm going to present today. I'm sorry for that, but we had a lot of terminology notation to be introduced. And it's one-line proof and trivial, anyhow. So this is conditional expectation. I'm using linearity. This is BT minus BS plus BS, conditioned to BS. And this is expectation BT minus BS, conditioned to BS, plus conditional expectation of BS, conditioned to FS. The future is independent on the present. So they are the conditional expectation, as I said before, if they are independent, then it turns out to be the expectation of a centered Gaussian random variable. filtration of BS with f of s. What is the filtration here? What is ft? Ft here is the sigma algebra. I'm sorry I didn't define it before. Is precisely the sigma algebra generated by BS for all s between 0 and t. Then, of course, BS is fs measurable. Then this is BS itself. This is a center Gaussian random variable, and this is BS. So we do get the property which we were looking for. Mind that, just a remark here. Mind that f, the probability restricted to f of t or f of s, say, allows to calculate probability of BS or BU in S for all U smaller than S, but not for U greater than S. I mean this filtration. This filtration is in fact amount of information we have about the process. So to have an idea what is, so we have trajectories here. We have S up to Fs. We can measure probabilities. We can measure probabilities on up to time S. But if we have U, which is further there, we don't have information what happens there. It's not part of the sigma algebra. It means it is in the future. We cannot predict the future. This is an interesting interpretation of filtration in terms of information. Now the p variation. 5 minutes, if you or 3 in 3 minutes. Then I finish. P variation for p greater than or equal 1. Given a function f from 0t into r, the p variation of f up to time t equals the limit when the mesh of the partition 0 Tn equals t. Equals 1 up to n f ti minus f ti minus 1 to the power p when it exists. And a few comments. If p equals 1, this is just the variation, the classical variation of a function. For instance, for differentiable functions with continuous derivative. So one variation. So this for p equals 1, f differentiable, which is far from our case, then one variation of f equals the integral of its derivative is the variation. But for p greater than 1 is completely, the reality is completely different. And we are going to prove tomorrow that one variation of martingales equals 0. And we have a fantastic lemma which says that if p variation of f exists in the sense that it's not 0 and it doesn't explode to infinity, then Q variation of f equals 0 if Q is smaller than P, and Q variation of f equals infinity. Sorry, this is the other way around. It's infinity if Q is less than P, and it is 0 if Q is greater than P. It means for each function f, continuous or not, mind that this p variation fits very well this continuous function. So for each function f, there could exist one p and only one p where we can calculate the p variation. All the others are not relevant, or either infinity or 0. So it's a decreasing function. P variation is a decreasing function with p, but with a very sharp, it's infinite p variation and 0. Compares with Hausdorff dimension, which for each set it has exactly one dimension where you can measure. All the others is not relevant. The point here is that if f is alpha holder, f alpha holder, it implies that it's 1 over alpha variation. It's a fantastic result which links both theory on Rawls path and p variation. The advantage here on the p variation is that, as I said before, is that this is in the realm of continuous function. This is in the realm of Cadillac functions which are continuous on the right and limited on the left. But this is there is this link on this. We carry on tomorrow. I'm sorry, I'm 3 minutes late. So thank you very much again for your presence. And I must say that you can interrupt me at any time to questions or comments. Please, it helps a lot. See you tomorrow. Bye. Thank you. The organizers have some instructions. Good one for lunch.
Hello, everyone. I'm going to have a lunch at the university restaurant. So if you guys want to join me, maybe I'm going to be able to get everyone in, okay?
Will you be doing the course with the slide? Is it possible that you send that to us? I you already. Okay, thank you. Thank you.
No, but I mean that's fine. But you're not because I thought that you right. So you like because I too feel maths related to rough farm study. Yeah, so I don't really understand, sort of the applications and rough farm. No, that's just you. Yeah, I know. I mean, I guess that I could ask Harry as well. I just wanted to. I don't really. Yeah, that's all right. Are you going to be doing homework at Gubinelli so you can look to yeah. If we can manage to reconcile that would be very, yeah. I think it's not.
Pergunta se Fábio Augusto não perdeu uma carteira. Fábio Augusto. Fábio Augusto. Okay.
Yeah.
Yeah. Okay.
Hi, so welcome back to the afternoon session. So before I present our speaker, I have two announcements to make. So the first is that the slides of this course have been sent to you via, well, WhatsApp, in the WhatsApp group, so you should check it out. And the second thing, is there Fabio Augusto here? Apparently he lost a card. So in case there's a Fabio Augusto here, you lost a card. Okay, so the card is at the reception. Okay, thanks. And I think then we can start. So our next speaker is Sebastian Riedel, who will give a course about rough path. And well, it's an honor to have him here. So Sebastian Riedel, he did a PhD with Peter Fritz, who is one of the guys who constructed this whole theory. And well, spent some time in Berlin for his PhD and postdoc, and is now a full professor at the Fern University Hagen. So well, thanks a lot for accepting the invitation, and go ahead.
Yeah, so thank you for the introduction, Dirk. So I was told that I'm allowed to remove my mask. I hope that's okay. So I'm very far from everybody. If it's not, so please let me know. So, okay. So yeah, so before I start, I would also like to take this opportunity to thank the organizers, Dirk and everybody else, for organizing this nice conference, this nice summer school, and of course for inviting me here. So it's a great pleasure. And so it's my first time in Brazil, and I so far I enjoyed it a lot. So thank you also. Yeah, and I would like to thank you here for coming, for listening to this talk or to this course. Yeah, I sent you the slides, or you got them by WhatsApp, so you don't have to take notes if you don't want to. You can concentrate on thinking about the things I present and concentrate on what I say, I hope. Okay, so this is the first lecture of 4. And the topic of this lecture today will be fractional Brownian motion. So it's a general, you will see that it's a generalization of the Brownian motion. The Brownian motion you discussed today in the stochastic calculus course. And so this process will serve as a motivation for rough path theory. And but before we come to rough path, I will present an easier theory, which is the Young theory, which is, I would say, very close to rough path theory. So Young theory, you will see, is quite old. It's from the 30s. Yeah, but somehow rough path theory is a generalization of this theory. So it's more close to the Young theory than actually, I would say, to E2 calculus, which was invented later. Yeah, so this is the plan for today. And yeah, in the next lectures, then we will proceed actually with rough path. Okay, so let's start. So the motivation will be the fractional Brownian motion. Then we will come to the Young integral. And the Searing Lemma, I will tell you what it is when we come to that point. So, okay. So the fractional Brownian motion was introduced also some time ago in 68 by Mandelbrot and Van Ness. It's a generalization, we will see that, of the Brownian motion, and it's a Gaussian process. So I don't know if you already seen a Gaussian process. So I give you a definition here to recall what it is. So a Gaussian process is a stochastic process, so in continuous time, and is also, does not necessarily have continuous trajectories, but so in general, it's just a stochastic process, which has the property that if you take some arbitrary points in time, t1 to tk, and then look at the vector xt1 to xtk, then you ask that this vector should be a multivariate Gaussian random variable. So that's it. And well, if you think of multivariate normal random variables, then you see that this Gaussian process is actually, or the law, is actually completely determined by the means and by the covariances, as I wrote them here. And this is simply because a multivariate normal distribution is uniquely determined by the expectation vector and the covariance matrix. And the covariance matrix only includes these covariances here. Yeah, so when you define a Gaussian process, you just have to specify these two things. And this is done here in the definition number 2. So this is the definition of a fractional Brownian motion. So it's a Gaussian process. It has 0 mean. So that means that all the expectations there at every time point are 0. Okay, and so we still have to say what is the covariance. And this is then written here. Oops. Yeah, okay. So this is the covariance. And in case that the process has 0 mean, this is just then the expectation of this product here. And so this is this term, which, well, the first one will not tell you much, I guess. What you see is that it contains a parameter, h. Yeah, so the h here is a parameter of this process. It's between 0 and 1. So it cannot be 0, cannot be 1. So it's between 0 and 1, and it's called the Hurst parameter also. So, of course, yeah, so you can claim, so you can, of course, give this covariance and then say that this should be a fractional Brownian motion. Of course, there are some conditions every Gaussian process has to satisfy in order that it really exists, but we will not do that here. So just believe me that such a process exists and that it has these properties here. Okay, so then you can calculate what happens for h equal to 1/2. And you will see that the covariance is just the minimum. So of S and T, covariance ST is just the minimum of S and T. And this is exactly the same. So this is what holds for the Brownian motion too, when you do the calculation. So we see that for h equal to 1/2, we just obtain the usual Brownian motion you just learned about in the course today in the morning. And here you see some trajectories. So a trajectory of a process means the following. So you fix some small omega, and the trajectory is then just a sample path, the path of the process. So this is a typical path of a fractional Brownian motion, a typical path of the fractional Brownian motion with different Hurst parameters. So you see for h equal to 1/2, we have this black trajectory there. Yeah, so this will be a typical path of a Brownian motion. And so then there are two different regimes we will see later, which are important. So one regime is for h larger than 1/2, one is h smaller than 1/2. So let's look at the typical path where the h is larger than 1/2, which would be the red trajectory here. So what this picture tries to tell you is that on small scales, yeah, this trajectory here wiggles less than the Brownian motion. Yeah, so it looks a bit smoother here on small time scales than the black trajectory. Yeah? And this will be indeed the case. And so let's look at an example. The small Hurst parameter, which is the blue trajectory, this wiggles much more, right? So one would expect that here the trajectory is rougher than a Brownian motion. You also see here in this picture that the red trajectory escapes from 0 here quite well. It could be, of course, yeah, it's a random process. It doesn't always have to be like that. But indeed, what you can show is that for the fractal Brownian motion, when you have a large h, then the trajectories will move faster, so with higher probability, more faster away from the origin. Whereas for small h, for small Hurst parameter, it sticks more to the origin. Yeah. So this is what we see here, and this is also indeed the case. We will not prove all of that. Yeah, but this is how it is. And yeah, it was introduced. Oh no. So yeah, the Hurst parameter, as you can see, somehow describes the behavior of the process. And one important thing, oops, so okay. Okay, so I have to stay here. Fortunately, the increments of the, you can say something about the increments of the fractional Brownian motion. So what you can say is something about the correlation. So you take two increments, yeah, of the fractional Brownian motion. So increment would be you take fractional Brownian motion at time t minus fractional Brownian motion at time s. And then you take two other time points which do not overlap with the interval s and t, and then look at the same increment. And then you can look at the correlation, yeah, and you see that they are uncorrelated for h equal to 1/2. This you probably already know, because this is the Brownian motion, and then the increments are independent, and so therefore they're also uncorrelated. Yeah. However, in the general case for the fractional Brownian motion, this they are not always uncorrelated. They are positively correlated for h smaller than 1/2. Yeah. And they're negatively correlated for h less than 1/2. And this is somehow, when you think about it, the reason why you could expect that for h smaller than 1/2, the process wiggles more maybe than for h larger than 1/2. So this you can actually really calculate if you want. I didn't do the calculation, but it's not hard to see, really, with the definition. So then you can consider the noise process. So what is the noise? So I would say the noise is the derivative of Brownian motion. So the derivative does not really exist for the Brownian motion because it's not differentiable, but still you can think about the noise as a formal derivative if you want. So if it existed for the Brownian motion, the noise process would have the property that at every time you have an independent random variable. So for every time in the continuum. So that's why you could call it white noise. Yeah. And so for h equal to 1/2, you had white noise, but for h not equal to 1/2, you don't have it. They're not independent anymore. There's no reason. Yeah, but that's why some people call it colored noise. Yeah. And yeah, so the fractional Brownian motion was introduced because often, many models, it's not so reasonable to assume that the system you want to model does not have any memory. So this is the case for the Brownian motion. Yeah, so every time you start, so the past doesn't matter for the Brownian motion. So in many models, this is reasonable to assume, but in many other models, it's maybe not. So think of, what did I say here, electricity markets, gas markets, everything. They're not very liquid markets, and they have a memory somehow. And these are examples where you could think of using the fractional Brownian instead of the Brownian motion to model certain things like price processes or whatever. Yeah. So what is a typical equation you would like to look at? Well, a typical stochastic differential equation would be maybe of this form here. So you probably didn't introduce that yet in the stochastic calculus course. It has a bit a weird notation when you're not used to that. Yeah. So here the d is something like the difference, but you don't write dy divided by dt, but for some reason you multiply. So you put the dt here. So it's just a different notation. But we will see in the next slide what actually should mean, maybe. So a typical SDE would be of this form, driven by fractional Brownian motion. So first of all, this would just be an ordinary differential equation. So not considering the sum here. This is just an ordinary differential equation, and the B would be, it's the coefficient in the equation. So it's a vector field actually. So here we would solve the equation in Rm. Yeah. So B is then a map from Rm to Rm. And you know from ordinary differential equations, so if this B has certain properties, for example, if it's Lipschitz continuous, this is a typical assumption, then the ordinary differential equation would have a unique solution. So, okay, so now something happened. Okay. Okay, but here for this stochastic differential equation, we have another term. So we do not only have the ODE, but we have also this noise term here. Yeah? And you can have, well, you can have one noise, but you also can have more than one noise. So here we have D noises. Yeah? So this is sum from 1 to D. And then you have some term here, the sigma I, that are also vector fields, so maps from Rm to Rm. And they might interfere with the noise here. So they might depend on the solution. Of course, they could also not depend on the solution. So in SPDE theory, you often make the difference, so to speak of additive noise or multiplicative noise. And additive noise would be the case where these sigma i's here do not depend on the y. Yeah, so this would be additive noise, just something coming from outside, so the noise is not affected by the solution. But when you have multiplicative noise, so it might be the case that the solution itself affects the intensity of the noise, for example. So this would be more, it's usually more complicated to solve also then. Yeah, so this would be a generic or a very general form of an SDE. And we will use, later on, we will often use this notation because I don't like to write so much coordinates. I use this short form here. So this is rather a scalar product if you want, in a product. This is d-dimensional, this is d-dimensional, yeah. Yeah, we solve this equation in Rm, and T can be, yeah, so we always look at initial value problems, so T equal to 0. Yes, and what do we assume usually? We assume usually that these driving noises, so the fractional Brownian motion here, so we have D of them, and you usually assume that all of them are independent. This is, of course, an assumption you can make. It's not, you can think of models where this is maybe not satisfied, but for simplicity, I will assume that here during all my course. Yeah, and yeah, so you aim at finding a solution which you call Y here. So whatever that is, so of course it will be a stochastic process again. It will be random because the B here, the Brownian factual Brownian motion will be random. So the solution will be a stochastic process. But it's at the moment, so as I wrote it down, it's of course not clear what actually a solution should be. Right? This is what we aim for. So we ask, what is a good solution theory? What is the good interpretation of this equation? So in other words, what should Y, the stochastic process, satisfy? What property should it have so that we call it, so that we can call it a solution? And not only, we want not only to call something a solution, but we would like to find a solution theory where such equations do have unique solutions, yeah, under some conditions. As you know, for ODEs, there are ODEs that have unique solutions, but others maybe do not. And so, yeah, so we would like to understand that. Okay. So there are several attempts now you can think of. How should we interpret this equation? Well, the first attempt would be the easiest, maybe you say, okay, maybe this is really just an ODE, a random ordinary differential equation. So an ordinary differential equation that has a random term somewhere, but okay, then we take this randomness, so we fix the omega and solve it for every omega. this would be this approach here. Yeah, so this is the usual ODE notation you're probably more used to. And so here I have this sum, and here I have the derivative of the fractional Brownian motion. So note that this would, although maybe you might think it when you only look at this here, this is a non-autonomous equation because you have a dependence on the t here in the equation through this process. So this is actually non-autonomous. Yeah, or would be. However, unfortunately, and that's why I do this course here today, maybe also is that this does not work because, simply because the fractional Brownian motion has trajectories that are too rough. They are not differentiable, almost surely. So they're, So you saw that already these trajectories there, they wiggled a lot, and you could have guessed just from the picture that they are not differentiable. And this is indeed the case. Nowhere. Yeah. Maybe you prove that for the Brownian motion, I'm not sure, in the stochastic calculus course, but this also holds for the fractal Brownian motion. There's one important remark, maybe. So there's another way you could go, but we will not go there. But when you stay here in this week, and also the next week, then you will attend maybe the regularity structures course, and this is exactly the way people in regularity structures go. That's why I wanted to do this remark here. So what is the remark? Well, when you do analysis, then if something is not differentiable, maybe you don't care. Yeah. So because you just look at the bigger class of functions, so you look at generalized functions or Schwartz distributions. And when you do that, then you can differentiate everything. Everything is differentiable of every order. But of course, you don't have a function anymore, but you have a more general thing. But if you attended to some PDE courses, maybe, there are some PDEs you can solve in such a way that you first enlarge the space of solutions. So you look at distributions, then you solve your PDE, and later you prove that the solution is not only a distribution, but it's really a function. So this you could do. And there's a question, why can't we do that here? So maybe, or why didn't people do that? So maybe we can take, well, oh, sorry. Oops. What was that? Okay. Mm-hmm. Hmm? Yeah, it's just, but I don't know how to use that. Wow. Okay. Yes, it's this one. Yeah. I don't know what happened, but okay. I don't know. That's fine. I can find it. Yeah. Okay. Thank you. Yeah. So we can say, okay, let's take this this noise process here, and let's assume that it's just a distribution, and try to solve it, the equation, in distributional sense. But then you will encounter a very serious problem in analysis, because what you want to do there in the equation, you would like to multiply this distribution, the derivative of the fractional Brownian motion, with the solution itself. So you could ask, what is, if you had a solution, what would be the regularity of this solution? And when you think a bit about it, you realize that the regularity is not, you cannot expect it to be better than the driving process itself. So this, you can just look at a very easy equation for constant coefficients, maybe no drift, and then you see that the solution would just be the noise. So there's no usually it will not be better than the noise. Yeah. And yeah, so what you want to do here, you would like to take the product of a distribution with this function, which is not smooth. Yeah, you cannot expect that this is smooth. And this is a problem, so you cannot do that. There's no meaningful description of the product, or not a good description of a product of a distribution with a non-smooth function. Yeah. And that's why people actually gave up that way and then moved to another approach. But yes, you will see in regularity structure that they will follow this. So the second attempt is then, well, stochastic analysis, so stochastic calculus. So you will see that in stochastic analysis, there is a good notion of a stochastic integral. Yeah, so, and this is called the Ito integral. You will learn about that in the stochastic calculus course. You can define the Ito integral under certain conditions. Yeah? So for example, for the Brown, you can, for x being a Brownian motion here, and for y being an adapted process, so adapted to the filtration generated by the Brownian motion, then this integral here makes sense. You can be more generous and say, okay, I just need x to be a semi-martingale. It doesn't have to be a Brownian motion, but then you can make sense of this integral. So then you could think about, well, if I knew what works for the Brownian motion, maybe it also works for the fractal Brownian motion. So I interpret this equation as an integral equation. Yeah? And I would like to make sense of this term here as an Ito integral. So this is done in stochastic analysis or stochastic calculus course. However, also in our case, this will fail because you know that for the fractional Brownian motion, this process is not a semi-martingale unless it is a Brownian motion. So unless h is equal to 1/2. So in all other regimes, it does not work. Okay. So although this attempt was extremely successful, so Ito theory is extremely successful and is still, of course, used in for many models because just the Brownian motion is so important. Yeah, so it's the most, I would say, the most important process, and it's very reasonable to use it for many models. Yeah, it's from the 50s, this theory, but it's still used today. So I don't want to make it bad. It looks maybe a bit that I say, oh, come on, it's not working here, but it doesn't work for the fractional Brownian motion simply. Okay, so there's a third attempt, and yeah, so this will be the topic a bit of today. This is the Young attempt. So there is a more general notion of a pathwise defined integral. So this is and now it's called the Young integral. Yeah, so what does the Young integral do? So you have two functions, f and g, and you would like to make sense of these two functions, of this integral, as an integral of Riemann sums. So you know the Riemann-Stieltjes integral, I hope. So it's defined, or you can define it as a limit of Riemann sums. So you take increments here of the g and take some point, say the initial point of the interval, the increment, and then take the sum. Then this is the Riemann sum, and then you let the increments getting smaller and smaller. So in the limit, you get the integral. And Young found out that, well, for the Riemann-Stieltjes integral, this works. This works in case the g had finite variation. So finite, you learn about the P variation, which is even generalization of the finite variation in the stochastic calculus course. And the F is continuous. So one, continuous is actually not, it can be very rough in our sense today. So has a very, can have a very small Hurst regularity or even no Hurst regularity. But on the other hand, the G should be very smooth. So one being of finite variation is for us today is quite smooth. And the Young integral is something in between somehow. So you can allow the F, so you can allow the G to be rougher than having finite variation if the F is a bit smoother. No? And okay, so today in the morning I heard that Paulo Rufino said that he is going to introduce the P variation because it's used in rough path theory. So he was completely right. It is used in rough path theory, but I do not use it today. So also not in the course, because I will stick to the Hurst case because in many situations it's enough. I didn't want to introduce more notation. I have to introduce a lot anyway. So I stick to the Hurst case. So I have to say that Young didn't look at Hurst continuous function, but he looked at P variation really. So there's a P variation formulation of this integral also. Okay, so this integral exists if the F and G are Hurst continuous and the Hurst indices sum up to a number which is strictly larger than 1. We will prove that also later. Hoppala. Okay, so now is the question, can we use this integral maybe? Can we use this integral for the fractional Brownian motion? So in order to do that, we would need to know something about the regularity of the trajectories of the fractional Brownian motion, right? And yeah, so you know, for example, that the Brownian motion, the regularity of the sample path, they are continuous. You can even say more, they have a certain Hurst regularity. We will see that here also. And yeah, we are now asked, what is the Hurst regularity of the fractional Brownian motion? And there is a classical theorem that will help us here. It's the Kolmogorov-Chantsov theorem. So it gives you, the Kolmogorov-Chantsov theorem gives you gives you a way to check regularities of trajectories. So take a stochastic process, and here in this formulation, I assume that you already know that it's continuous. There are formulations where you don't. I will come to that after the proof of this theorem. Now let's assume that we already know that a process is continuous, has continuous sample path. That's the case for the fractional Brownian motion, for example. And then assume that you have certain estimates of the trajectory here. Sorry, of the increments. So, and the estimates are in LQ. So LQ omega. Yeah. So if you know that this holds here, the xt minus xs in LQ norm is smaller than a constant times t minus s to the beta. Here I restrict to the case that ex is only defined on a compact interval. Okay, for this is the condition. So what can you conclude? Then you know that for all alpha being less than this number here, so it depends on beta. Beta is this parameter. It depends on q, which is the so the q norm here. You know that there's a random variable being in this in AQ such that this holds here actually for every omega for all st in 0, 1. And in particular, so when you know that the k alpha is in AQ, you know that it's finite almost surely. So in particular, the trajectories of this process are almost surely alpha Hurst continuous. Okay. So this is the theorem, and a corollary, an immediate, is now present here. So you can conclude that the trajectories of the fractional Brownian motion are almost surely alpha Hurst continuous for every alpha strictly less than 1/2. Yeah. So for the Brownian motion, take h equal to 1/2. And then this theorem tells you that for every alpha strictly less than 1/2, yeah, the Brownian motion has a trajectory of exactly this regularity, almost surely. Yeah, you can even say more. A side remark, you can even say more about the Brownian motion. So there are very precise statements about the regularity of the trajectories of the Brownian motion. We will not use them here, but if you're interested, I don't know, do not think that we will do that in the course, but there are many books, for example, from Revue where they prove this kind of statements. Very nice. Yeah. Okay. So what is the proof? Well, we just use the definition of the fractional Brownian motion. So here, you could even, I think, write equal to if you say what is the C, what is the constant here. Because this is just the definition, you can just use the definition of the covariance function of the fractional Brownian motion, so in L2. So when you plug that in, you see here that this can be bounded by t minus s to the h. H was the Hurst parameter for every s and t. And now, since the BH is Gaussian, you know that this increment, BHT minus BHS, is actually a normal random variable. And when you can bound the L2 norm, you can also bound the LQ norm here for any Q larger than 2, say. The price you have to pay here is that this constant might get larger. Yeah. But it doesn't matter, because then, so you have the same result here for every Q. And now when you go back to this statement here, so the beta was equal to the h in our case, and the q you can let tend to infinity, and then you see that the alpha can be chosen arbitrarily close to the h, if you want. Okay, so that's it. That's the proof. So in principle, we can, there's hope that we can use the Young integral because we know something about the Hölder regularity. But before we proceed now, I would like to give you a proof of this, of the Komogorov theorem, because it's also used later in rough path theory. There will be a version of it in rough path theory. And so I would like to remind you of the proof, or maybe you see it the first time. Yeah, so this is the proof of the Kolmogorov theorem here. So without loss of generality, we take t equal to 1. You can always do that because you can rescale the process if you want. So after rescaling, the regularity, the Hölder regularity does not change. And so now we introduce these so we introduce the dyadic numbers here. So dn, oops, so the dn are just the dyadic numbers. Yeah, and then no, they are not the dyadic. The d's are the dyadic numbers here. Okay, the set d contains all the dyadics, and then we define random variables, and the random variables are suprema of the increments of the process here. Kn is the supremum here, this process. So here I introduce this delta notation. Yeah? I will use it also later. That's why I wanted to already introduce it here. The delta, when I write then 2 indices here, just means that the increment notation here. Okay, so dn bar, the absolute value, just means it's the smallest, so the size of the partition, the smallest size between these consecutive points in the partition. So in this case, put the 2 to the minus n. Yeah. So then we do the following calculation. So we try to estimate the expectation of the kn to the q. Yeah. And so we have a supremum, which is actually a maximum. So I wrote supremum, but you can see that are only finite numbers. I take the supremum there, so we can also switch to the maximum. And this maximum can, of course, bounded by just the sum of all these terms. So a very stupid estimate. There are many very stupid estimates in this theorem. You can think about that. It's interesting that you still get a very precise result later. Okay, so So you can estimate this by the sum. This is done here. Yeah, and then you use in the next step, you just use your estimates for for the increment. So this is here. This is this estimate, and then you have just this number C. This is the C, the assumption to the Q, and this 1 divided by dn. These are the numbers of t's here in the dn. Yeah. And yeah, so what you end up is then this term, okay. And so now comes an important point. So you take now two dyadic numbers in D, and you assume, so you take two dyadic numbers S and T, and you assume that they difference here satisfy a certain property, so that there's an M such that the T minus S lies exactly between these two numbers here. Okay. Okay, so now what you do now is so somewhere here in between are all these dyadic. So for dm, so there are all these dyadic numbers, and so yeah, they get smaller and smaller, but they are contained in each other. Yeah. So what you do now here is you take S and T, and then you take the coarsest. So you take two numbers. So you take now points in this partition tau 0 to tau n in such a way that you now try first to take the coarsest. You start with the coarsest partition and take, so this would be in this picture, this one here, and you put this in your choice. So you take these tau, say I, and tau I plus 1. So you start with the coarsest partition. And then you take the next finer partition. So this is then maybe that one, and maybe that one here. And now what can happen is that you have, so this is then another tau, I don't know, this is another tau. Oops, no. What can happen is, here in this picture, is that the distance between these two taus and these two taus is the same. Yeah. And then you take the next finer, and then you have maybe something here, or maybe something here, and so on, until you reach these points here. And you will reach them by assumption. When you do that, then this partition you chose here has the properties that at most two intervals here have the same length. And not more than two intervals have the same length. Yeah. Okay, so this is the clever partition, and when you do that, you have the following. You can now estimate this increment here. So, okay, so the first estimate here is, of course, just the triangle inequality. And now you estimate all this inside here by the length of, by the length of these intervals. And the Kn, remember, was the supremum, was the maximum of all these things. So you can estimate all this here by a certain Kn. So and then n, you know that it has to be larger or equal to m plus 1. And the 2 here is, you have that here because you know that at maximum 2 intervals have the same length. That's why you have a 2 here. Okay. So in total, what can we say now? So when we estimate, then yeah. So this term we want to estimate. Then first of okay. So this we just saw that. Yeah. So we can use this estimate here, and the t minus s to the alpha can be estimated by dm plus 1 to the alpha just by this choice here. Just by this choice here. Because the dm plus 1 is smaller than t minus s. So it was here. Okay, so next, then you say, okay, I don't want an m dependence here. So I replace the m plus 1 just by the n. And this is okay because also it gets even smaller. So you do that, and then you say, okay, I really want to get rid of the m here, so I just start this infinite sum. So this quantity here you call k alpha. It can be infinite. At the moment, we don't know. Yeah. So what we have shown then is this estimate here. So for fixed, so here omega is always fixed. For fixed omega, we can estimate the increment by k alpha, this quantity times t minus s to the alpha, for every s and t in the dyadic numbers. This was important still. We only have the dyadic numbers, so s and t are not arbitrary. Okay. So, but now you can use the continuity of x. So we knew that it was continuous. So this estimate actually holds for every s and t in the interval. Okay. So what remains to do is to for the Hurst regularity, what we still need to prove is that this k alpha here is, so it's a random variable, this is clear, but we don't know if it's a finite random variable, almost sure. So we have to prove that, or there's even a stronger statement that it's not only finite, but it's actually has finite Q moments. This is what we need to still to prove. And yeah, so this is done here. So the k alpha in AQ can be bounded by this term. And so when we go back here, yeah, so this was, sorry, so this was just the, oh, it's not the definition because we already take the AQ norm. So you use the triangle inequality for the AQ norm here at this point in the first estimate. And yeah, and then, well, you just plug in what you already estimated before, the Kn in a Q norm. Let's go back. So where, yeah, it was here, you see. So this line here, so you plug that in. Yes. So you finally, and this is what you, when you plug in what you see, but the dn was just simply 2 to the minus n. Yeah? And this is summable by assumption on the alpha, because the alpha was chosen in such a way that it's smaller than the beta minus 1 over q. So in total, this is a positive, strictly positive exponent, and that's why this is summable, and therefore in Q, LQ, this random variable. So in this proves the theorem. So yeah, now a remark. So often the Komogorov Chernyshov theorem has another formulation where you do not assume that the x is really continuous, but you use this theorem to prove that a certain process, for example, the Brownian motion, has a continuous modification. But the proof really works exactly the same. Of course, there was one point where we used continuity, and this was when we had these estimates for the dyadic point, for the increments of the dyadic, taking points in dyadic numbers, taking time points in dyadic numbers. Then we said, okay, from continuity, we can take any point actually. This, of course, we cannot do. And in the proof where you do not use them, you define then another process, x tilde, which Yeah, and this x tilde coincides with x on the dyadic points, but then you extend it continuously to all these points. And this, of course, can now be different. So can be another process that the x, but what you can prove is that it's still a modification of the original process. And also, I should say here that the Komogorov Chensov theorem, I didn't write it down, but it also has a formulation not only for stochastic processes, but for processes having just a time parameter. So you can also, there are proofs for processes having where the t is not in an interval, but can be in a square or in a cube or something. So you can look at a stochastic, I think you call it fields if you want. So there's also a proof for, there are some conditions where you can prove that we have certain continuity there. What is important is that it does not work for t being in an infinite dimensional space. So then the theory breaks down. So the t, in the stochastic process, for this theorem to work, has to be taken in a finite dimensional space. Of course, the argument here gets then a bit more complicated. It's not, we will not need this generalization here. Okay, now is the second part of the talk. So the Young integral and the Sewing Lemma. So the Young integral we have already seen. And we want to give a proof of Young's theorem. And we will do that by proving another very important result in rough path theory, which is the Sewing Lemma. And this is really a cornerstone, not only, so it's we will see that can be used for the Young integral, but can also be used for rough path in many, many situations. So it's a very important theorem. And so to formulate this, we will introduce some notation. So so we take a Banach space, or a linear space, actually what is important here, a Banach space. And so first notation is the C will denote the space of continuous functions, taking values in this Banach space defined on the interval 0t. And then we will often use this increment notation here. I already used that. The delta, so when you have a one parameter object here, so a path here, when I write the delta, I get a two parameter object, and this is just an increment. Then C alpha here denotes the space of Hölder, alpha Hölder continuous functions. So that means that this norm here, it's actually it's a semi-norm, but okay, so but we still use this norm notation. So that this quantity here is finite. Here the S and the T are allowed to take any value, so in 0t, but of course they should not be coincide. Should not coincide. And then, so these were Hölder spaces, and then we will also introduce this space here. So these are functions that are defined on having two parameters here, S and T, and so they are defined on the simplex. And we assume that first, that when you take T and T, so when they are the same, this should be 0, like for increment of a path. And then we introduce another quantity for this, so another kind of norm. So alpha beta means, alpha norm, or actually I should say semi-norm, but in this course I will often say norm, I think. So alpha norm of this plus beta norm of delta of this xi here, this xi. And what is all this? Well, the alpha norm is exactly the same as you do for paths. So for path, you would look here at an increment. So this doesn't need to be an increment. This is just a 2-parameter function. Yeah? But you define it exactly as for the Hurst norm. And then we introduce first a delta of this 2-parameter function. So what you do is you take SUT, and so usually the S is smaller than the U, smaller than the T. So you take here ST minus SU minus UT. If this psi here would be the increment of a path, so what you see here is then this would be 0, because you take the increment of T minus X minus U minus S minus U minus T. So this would be 0. But in general, it doesn't have to be the case for just any 2-parameter function. And then we define this beta kind of norm here. And so S smaller U smaller T. And then here you just take T minus S to the beta. So the U doesn't play a role here in this fraction below. Okay. So fair enough, you can do that. And now we can formulate the Sewing Lemma. Okay, so you have 2 parameters, alpha and beta. And what is important here is that the beta here is strictly larger than 1. And then there is a unique continuous map taking a 2-parameter function here, mapping to a 1-parameter function. Actually to the Hurst space of 1. So a function that are alpha Hurst, such that the following is true. So there's a unique, it's continuous and it's unique, having these properties. So first of all, so this is called I of psi at 0. So it's 1-parameter function. You can evaluate it here. Is I forgot to write. It's equal to 0. Sorry. So here I forgot equal to 0. And you have this estimate. So, okay, so what is this? The I here is a 1-parameter function, and then you can apply the delta, then you have again a 2-parameter function. Yeah? So you can write ST here, and then you can look at the difference of the original psi ST, and this can be bounded by C times this norm here, this beta norm, times T minus S to the beta. And C depends only on beta, as we will see in the proof. So this is the Sewing Lemma. It looks very abstract, but we will see in application how you use it. And the I here, I should already say here, is really should remind you of integral. So it's an integral map actually. Okay, so let's prove this theorem or this lemma. So we start with uniqueness. So assume that we have 2 of these maps here, and assume that we have 2 I's. So the I are now these objects. So the I is I of psi here. So this I here would be I of psi, and I tilde would be another map I tilde of psi. And if they both satisfy this estimate here, then we can use the triangle inequality to see that this difference here is less or equal to C times T minus S to the beta. Yeah, so the C is not the same C as here, but here in the C are, so I put inside the norms here also. So it's not the same. Not the same C, but it's some number which is smaller than infinity. Okay. So what do we know now? Well, we know that first of all, by assumption, the beta is larger than 1. Beta is larger than 1. And we know that the I is a path, same as I tilde is a path, because of this mapping here to the 1-parameter objects. So also the difference I minus I tilde is a path. And what we see here is that this path has a beta Hölder regularity for a beta larger than 1. And this, well, maybe you know about this Hölder norms. If you don't, well, you introduce it only for parameters smaller than or less or equal to 1, because it's not interesting for beta larger than 1, because then if the Hölder norm here is finite, it means that this path was just constant. Yeah. So we know that the increment here is constant, and we also know that they both start in 0. So this is what I forgot to say here. They both start in 0, so they're constantly 0. So the increment is constantly 0, so they're both the same. Okay, so this was uniqueness, and now comes existence, and existence is a bit harder. So let's fix an interval as t and a partition, and now I just take any partition. So I'm allowed to take any partition here of this interval. So so the absolute value of p denotes the maximal length between two consecutive points in P. So it's this quantity. This is actually consistent with the notation before in the Komogorov theorem. If you go back, it's the same. But the Komogorov theorem was a bit easier because I only took dyadic partitions. Okay. So then here also use integral here. So I take the sum of these kind of increments here. Oh, well, it's a 2-parameter function, so it doesn't have to be an increment of a path. It looks a bit like that, maybe. Yeah. Okay, so we introduce this, and the idea will be, okay, so these are just, it's now an element in W, and we want to bound this element here. So we want to introduce, so to find an equality, a bound for this object here, which is uniformly in P, uniformly in the partition. So this will be the crucial point. And we will do that by, the idea will be that by removing points. You will see what I mean soon. Okay. So the claim here is that if R is larger or equal to 2, so R where, okay, let me go back, the number, well, not really the number of the points in the partition, but the number of points in the partition plus or minus 1 plus 1. Yeah. So here's the R. Okay, so if R is larger than 2, then there is one point in the partition such that for the neighboring points, so the left neighbor and right neighbor, we can estimate the difference of these 2 points here bounded by 2 divided by R minus 1 times T minus S. Okay, so why should this be true? Well, otherwise the following would hold. So we can look at 2 times T minus S, so the length of T minus S here. And when you have S and T, so what you do now is, so you have your partition, and what you do now is you take one point here and you sum up the differences here. Yeah. And so when you do that, you do not get the length of S of T minus S, but what you get is 2 times the length, because you always count intervals double there. So this is the first estimate. So this is the first estimate here. And then you assume the contrary, on the contrary, that these are all less than the quantity on the right-hand side. So this would give you this lower bound here. if this was not true. But this is, of course, a contradiction. Okay. So let's take this choice. So let's take this u here, and let's look at the difference of these integrals, or actually sums. No, they were just sums. And when you see that, well, most of them will cancel because you just remove one point. Most of them will cancel, but there will be one what is left, and this is exactly this thing here. No? So this delta. And yeah, for that we use our estimate we assume to have. So this was the condition. And so finally, and yeah, so in the next step, yeah, we just, yeah. So having that, so we use this estimate here, so the claimed, what we claimed, plug that in. Okay. So this is what we do now. So we have the integral, yeah, and then we remove one point. Okay. So we use the triangle inequality, then we have the integral again, and then we remove another point, and always this point with this, which had these properties there. So this is how we estimate this quantity. So we remove points, remove points until we reach this this term here. And so what changes? So how do we bound all these terms then? Let's go back. So we always bound it with this number here. And what changes is the R, because the R were the number of points in the partition, and they of course get less and less. When we do that. Okay. But here we want a uniform bound. So that's why so usually you would start here. So if you have R points here, then this would not be infinity, but this would be an R here. But we want a uniform bound in R, so that's why we bound this again by infinity. And yeah, so this is just the zeta function. So that's why the zeta here, Riemann zeta function of beta, which is finite since we assumed that beta is larger than 1. So this was the maximal inequality we wanted to establish. So you see on the right-hand side, so the right-hand side is finite, it is independent of the partition. So the goal is to define the I map here as the limit of these integrals when the partition gets smaller and smaller. So this is the goal. And we already almost have it. So what we need to prove, or for this goal, what we need to prove is this condition here. Certain, like a Cauchy condition. This is what we need to prove that this really has a limit. And for proving that, we will need the maximal inequality. That's why we prove that first. Okay, so to prove that this here holds, what we can do is, of course, we can use again the triangle inequality and introduce another partition, which is just the union of these two partitions. And so without loss of generality, we can assume here in this statement, when we prove that one partition is contained in the other. Okay, when we have that, then we can really calculate the differences of these sums here. And yeah, so then again, a lot of them will cancel and some will remain. And when you think about it, what will remain is exactly this one. So one is the, so you have a sum of uv, and then you have some, oh, no, they're not canceling yet. No, it's just the definition, just the definition. It's just the definition of the differences here. So this is the finer partition here, the P. Okay. Okay, so of course, when we have the finite partition, the maximal length between these 2 points here. Sorry, is that really correct? P is this finite partition. So maybe there's a typo. There's a typo, yeah. Sorry for that. So this should be a P prime here. It should be a P prime. I hope it doesn't. Well, we will see what happens. It's fine. Okay. Thank you. Then okay, thank you. Yeah, that's fine. Okay, that's good because it's actually really important. Okay. So yeah, so what we do now is we use the maximal inequality. So now was here to bound these terms here. Let's go back maybe to see. Yes. Okay, that's why we have a 2 now. Okay, so to be honest, I don't see at the moment why, but you can probably have a look and check yourself. So here you really use the maximal inequality. Yeah, the v minus u to the beta is of course, yeah, is then t minus s here would be t minus s. Yeah, it's just the sum. That's just the sum. For every term you use this for every term you use the maximal inequality is fine. Oh my God. This you should. Sorry. Okay, no need. I can. Okay, perfect. Okay, very good. Perfect. Okay. Yeah. Okay, so now, okay, you have all this stuff here. All the stuff here doesn't matter so much what it is. It's just finite. And then you have this sum here. Okay. And you have a beta which is larger than 1. Yeah. And then this sum here is a big O term of this order here. Because you can just take the maximum size of this if you want and put it out. And what remains here is something which sums up to, I think we were on 0t or 0.1, I don't know, but sums up to a finite number. Yeah, so finally you see you have something here which really goes to 0 when the epsilon goes to 0, and this was the claim, and this also was the proof now of the Searing Lemma. So this was all we needed to show. Okay. So we saw also that this map here is actually quite explicit. Namely, it's the sum of these increments of this. No, it's the limit of these sums here. This will be really Riemann sums in the application. Okay, so now comes the application. So Young's theorem. So we can also prove that quite general in Banach spaces. So G is alpha Hölder, F is beta Hölder. We assume that alpha plus beta sums up to a number strictly larger than 1. Then I claim that this integral here exists as a limit of Riemann sums for every S and T in the interval. Okay, so how you do? Sorry, there's another statement. You can also estimate this, this integral here by a term, and what will be important is that we have t minus s to the alpha plus beta here, which is assumed to be larger than 1. Okay, so this theorem now is actually, the proof is very fast. So you just define now the Riemann sum. So the psi st here is just f of s applied to gt minus gs. So what we can go back here So G took values in V, and F took values in the linear space of V to W. So that's should be that's correct, yeah. Or maybe I think I mixed that up. So it should be the other way around. Sorry, I will change that. So G should take values in this space, and F should take values in V. That's correct? Again? Yeah, you apply it. Yeah. Sorry, yeah, okay. That's correct, okay. Okay, so then this is an object, this is an element in W. And so you apply now these, the definition of the delta here, and you write down what is all this. Yeah. And then you see that it's exactly, I do the calculation, and it's exactly this one here. Okay, so we can estimate now the alpha norm of psi here, which can be bounded by the alpha norm of G times the supremum norm of the F. Which is of course finite, because we assume that G is alpha Hurder and that F is continuous. That's all we need here. And we can also estimate the delta here. And here you see when we have T minus S to the beta here, we can now, we have T minus S to alpha plus beta. And this can be bounded then by the beta norm of F. So take one part is the beta, and then you have the alpha here. And total, what you get is that, yeah, so this can be estimated by the product of the norms, of the Hurder norms of these functions, which is finite as well by assumption. And that's it. So now we can apply the Sewing Lemma and define the integral just as here. The I would be the integral, and the delta would be the increment of the integral. So you have S and T here, Fu dgu. And yeah, the bound is just the bound of the Sewing Lemma. So when we go back here, convince you. So this was the bound, and in the Sewing Lemma, so you had the beta norm here of delta xi, which we could bound by the alpha norm and the beta norm, the product. Then we have C and T minus S. Then we had alpha plus beta in our case. Okay. Okay, so this was the Young integral. Now, we can now make or try a definition of a differential equation. So we take actually a path here for the moment. We take a path here, we take a collection of vector fields, we take an initial condition, and then we say Y is a solution to the Young differential equation if and only if Y satisfies an integral equation. This integral equation here, where the integrals we want to interpret as Young integrals. So this is a definition we can make. And the theorem is now that provided the X is a path, it's not a stochastic process yet for the moment, provided the X is alpha Hurder for alpha strictly larger than 1/2, provided that sigma, the coefficient here, is sufficiently smooth and bounded for the moment with bounded derivatives, then this equation interpreted as a Young equation has a unique solution for every initial condition. This is the theorem. And I also want to give you the proof because this is exactly what we will use for rough path as well. So this for rough path will be the same strategy. We will define a notion of an integral, and to solve a rough differential equation, what we will do then is just perform a fixed point argument also on certain spaces. So let's see how that works here in this relatively easy case. So we first restrict to a maybe smaller time. So we had an interval 0t here. T0 is between 0 and t. So maybe it could be a bit smaller, could be smaller. And we define a map for a Hurst path here, alpha Hurst path, which is defined as here. So it's again a path. And so we would like to define it like that. So y is a path. We would like to define this as this integral here. And so integral driven by x. T is between 0 and t0. So it's again a path. So what do we know here? Well, we have to make sense of this first. Yeah, it's not completely obvious how this integral here is defined, because all we know is that the alpha here is C alpha. We assume that the y here is C alpha. We assume that the x is C alpha, but we apply the sigma to the y. So we make a so we apply this function to y, and we still have to say, well, what we have to check is that this path here is again has the right regularity. So it has so now we have to assume something on the sigma here. We assumed Lipschitz continuity. Since sigma is Lipschitz, it's easy to see that the path here is again alpha Hurst. And so we can really define this integral here as a Young integral. Yeah, because both here are alpha Hurst, y is alpha Hurst, x is y is alpha Hurst, and the alpha is larger than 1/2. This is an important condition here, because then alpha plus alpha is really larger than 1. Otherwise, this integral would not be defined. So we can define this map here as a Young. So this is a map we can define here with this map here with the help of the Young integral. And we also know something about the regularity of the Young integral. So we had this bound, if you remember. So the bound was quite strong. And in particular, it implies that the integral itself here, so the integral itself here only in t, so this path here in t is again alpha Hurst. Yeah. So what you can see then is that this map here, the empty, is in fact a map from this, from the space of alpha Hurst path to the space of alpha Hurst path, starting in y. This is what the y indicates. Y was the initial condition. Y was the initial condition. Well, you can check that again if you want, because when I start with the y here, which is starts in small y, and for t equal to 0, this integral here just disappears, so it also starts in y. So these two maps map to the same. This map here maps from this space to itself. And what we want to show now is that this map is a contraction. So these spaces here are not Hurst spaces anymore because we fixed the initial condition. So they're not Hurst, but they're still metric spaces with the Hurst norm. Now really, this is a metric. Yeah. So when we show that this is a contraction, we can use the fixed point theorem to prove that this map really has a fixed point, and the fixed point is exactly the solution to the space, at least, to this equation, at least on 0, t0, so on the smaller time interval maybe. Okay, so let's look at the difference here. This is what we have to do. Let's look at the difference. So the difference, then this initial condition, of course, cancels. So we just have the integral here. And yeah, so we can bound. We can now use the Hurst, the bound for the Young integral. So yeah, this you should check for yourself. So the bound I gave you looked a bit different because we also had we subtracted some term from the Young integral. Yeah. But you also get a bound for this term here by just applying the triangle inequality, but then you also have to consider here the supremum norm of this. That's why it pops up here, not only the alpha Hölder semi-norm. Times the alpha Hölder norm of x times t minus s to the alpha. Also, here only have t minus s to the alpha, not 2 alpha. Okay, now comes a bit something, well, you have to go through yourself if you want. So here you want to estimate these terms here, especially this here, by just the difference Hölder norm of y and y tilde. So this is a bit, you have to do some calculations here. And you need the regularity of the sigma here. So we assumed here that it's not only differentiable, the sigma, but it's only even 2 times differentiable and it's bounded. And this is what is needed here in this, for getting this bound here. Okay, so what do we have now? So we have some constant. Okay, so we have the rough path, t minus s to the alpha. And this is nicer because this is exactly the norm or the metric. So this is the distance between y and y tilde. This is what we want. But of course, it's not clear yet. So here I wrote it again. So yeah, so this is what you get then. So here we have the alpha Hölder norm. So because we have t minus s to the alpha times here this constant and times the alpha Hölder norm of difference here. So, okay. So what can we do? So remember we want to, yeah? Here, yeah, this was something, okay, so maybe let's go back. So let's look at the bound for the Young integral. So we need it, okay, here, yeah. So what we want to bound is only this integral, not this term. And bound only this integral, what we use the triangle inequality, so we subtract this term here and then we add it again. Yeah? And when we add it, to bound this here, we bound it by the alpha Hölder norm of G times the supremum norm of Bf. And this is why this pops up. Yeah. Welcome. Okay. Yeah, so we have this here. So what the good thing is that C can be chosen independently of T0 and also independently of y tilde. But nobody tells us that this is smaller here than 1. And this is what we need for a contraction. So what we cannot just do, unfortunately, is to choose the T0 small so that we can expect that this gets small too. This is not true because an example would be take the alpha, so 1/2 Hölder norm of the square root. So this is not getting smaller when you take a smaller interval. So therefore, we have to, it's a bit the technical thing, but what we actually do is then we choose an alpha prime, which lies here. So it gets a bit smaller than alpha, but still larger than 1/2, and repeat all what we did for the alpha prime. So if x is alpha Hölder, then we can indeed conclude that in this weaker topology, then that this goes to 0 when T0 goes to 0. Yeah, exactly. So then we can prove that MT0 is a contraction on this actually a bit larger space. Yeah? Okay. But then, sorry, no, okay, on this, sorry, here should be a T0 also. So this, now we can conclude that it has a, this equation has a unique solution on this space, well, on this small, on a small T0. And now you do something you also do in ODE theory. When you have a solution only on a small time interval, you can restart. So on the interval next to it, so T0 to 0 to T0 here. Then it's important that the T0 here does not depend on the solution or something, or on the length on the solution. So, and then you can do it again and again and again until you reach finally, eventually, the whole interval. You glue together this solution and you have one. Also gives you a uniqueness. And okay, so still we have a unique solution in the alpha prime space. But what we can do is we can check, having the regularity of the Young integral, we can check that the solution is actually even alpha Hurler continuous. So we can have a kind of a priori estimate gives you that. So this finishes the proof. So I'm almost done. So in total, what we can prove now is that having a fractional Brownian motion where the Hurst parameter is larger than 1/2, because otherwise it doesn't have the right regularity. If the sigma here is sufficiently nice, then we can solve this stochastic differential equation as a Young differential equation. And we do that by solving it for every trajectory. So we fix a trajectory, so on a set outside measure 0, and we know that it has the right Hurger regularity. Then we solve this equation for this fixed trajectory, we get a solution. Okay. So this is what is called a pathwise solution theory. Yeah? So you can solve this stochastic differential equation, this SDE path by path. Yeah? So in particular, what you see, if the fractional Brownian motion is alpha Hurler continuous outside a set of measure 0, exactly in this set, you can solve this equation. This might look trivial to you if you've never seen that before, but when you follow now the course for Ito theory, or you saw the Ito integral, then this is really different. For Ito's theory, you know also that the Brownian motion has continuous trajectories almost surely, but when you solve your equation, you get a new null set, maybe. You get a new null set on which the solution is defined, or not, so outside the solution is defined. So in particular, the solution somehow depends on the whole equation. It depends on can depend on the initial condition and also on the vector field. So another initial condition, for example, could lead to another set of full measure where the solution is defined. Yeah. And since usually the allowed initial conditions are not countable, it is for Ito's equation, it's not clear. Yeah, it's not clear whether there is a set of full measure on which you can solve the equation that is independent of the initial condition for Ito's theory. For a pathwise theory, like here for Young's theory, this is immediate. Yeah. And if you follow the course of stochastic calculus, I saw today that you're also going to speak about stochastic flows, for example. So this is a problem when you use Ito theory, so to establish the flow property, where for a pathwise solution property is almost immediate, so the flow property. Okay, so I'm done with my first course. So here I want to give you some references if you want to read up something. So here, this is the paper where they introduced the fractional Brownian motion. If you are interested in more properties, maybe a bit more modern approach, then I can suggest you this book here, Stochastic Calculus for Fractional Brownian Motion. There you find all these properties I just stated here without proof. Then the paper where Young introduced these, his Young integral is from 36. Actually, I think he really had the same idea with this removing points for introducing the Young integral that I used for proving the Sewing Lemma, which is somehow interesting because the Sewing Lemma is really now the core of rough part theory. So if you want, it was already there, or some parts were proven in 36 already. So yeah, so this, why did I put Gubinelli here controlling rough path? yeah, because he proved the Sewing Lemma, so he formulated the Sewing Lemma first time. But I think he took another proof as young. It's a bit, I don't know why, but I think it's not with this removing point stuff. The proof I took for the Sewing Lemma is from this book here, Fritz Heirer, Course on Rough Path. I will use many, many things from this book here. I think it's a very nice one. Yeah. Okay, so this was all for today. I thank you very much for listening. Mm-hmm. Mm-hmm.
In principle, you okay. Yeah. Okay, so sorry. Yeah, so in this lemma you actually prove that the solution operator is continuous in this alpha prime topology.
I'm not sure if I really proved the continuity, but
Yeah, well, okay, but in principle you prove that the solution lives there in C alpha prime, right?
yes.
Can you actually a posteriori, knowing that there is a solution in alpha prime, recover a solution in C alpha?
So what I did was I wanted to prove that a solution lives in C alpha, but what I did first is I proved that the solution lives in C alpha prime, where the alpha prime was smaller than the alpha, but still larger than 1/2, which was important. Yes, so this is a weaker statement. But then a posteriori, what you can do is when you look, let me maybe go back to what is actually a solution. What is a solution? Oh no. So, okay, yeah. So this, so I found a y. I found a y here satisfying this equation. And now a posteriori, I can take here an increment yt minus ys, and then I have just an integral here, t minus s. And yes, and I know that this integral here has the right regularity. It has the Hölder, the alpha Hölder, so the right regularity. So a posteriori, I can really prove that the solution has the right regularity. Yeah.
Thank you.
Okay.
Are there more questions?
In the uniqueness proof, when we use Hölder regularity, we can do this fixed point argument. Does the same argument work if we work in the p-variation framework?
Yes.
Okay, it works precisely the same way.
It's exactly the same.
Okay.
Yeah.
Okay, I didn't see right away.
No, I think, no, I think so. It's really p-variation and Hölder are almost interchangeable.
Okay, because I wasn't sure, because you just work with these increments, so you can divide by t minus s and you get the Hölder norm, but with p-variation.
Okay, I would have, I mean, I'm almost 100% sure, but of course I would have to go through proof, but I think it's fine, yeah.
Okay, thank you.
So just off the back of that question, can I ask you where you drew the proof of the uniqueness from, or just a whole proof?
The whole proof of the Young.
Is that from Baudouin's lecture notes?
It's actually from Terry Lyon's lecture notes, I think. So, okay, I know that in the Saint-Flour lecture notes from Terry, he proved that Young differential equations have unique solution under certain conditions. So this, I think he did the same, more or less the same proof. Actually, in this lecture notes, he does it. So, okay, when you check, it's a bit delicate because he does it for in Banach spaces, even so infinite dimensional spaces. And here, I didn't write it down, but I think it works only for finite dimensional spaces.
So yeah, that's indeed a subtle difference, but the terminology Young differential equations
Yes.
and the use of finite dimensional spaces is actually one that was sort of Young differential equations was coined by Baudouin.
I think Young didn't prove. So I think he didn't consider a Young differential equation. He just defined the integral.
Yeah, so that's by Baudouin, and so in the same Fleur-Neck you have to assume that sigma has a regularity strictly greater than 1, and it's actually false. And it's actually false that there is a unique solution when sigma is equal to 1, because in the uniqueness argument where you sort of bound the alpha norm of that difference, it's not true that you can bound it by k times y minus y and the alpha norm of that difference. There's counterexamples to that.
So then can you say again? So you think it was not correct? Or?
I don't think so, no. I think you need to assume that sigma is lip alpha for alpha strictly greater than 1.
No, but I think I assumed that it's C2. So I even assumed more, I think. Let me see, twice continuously differentiable bounded derivatives.
But
I think this is even more, so it should be enough when I'm not wrong.
Right. It might be true then.
I mean, I think you can weaken this. You can weaken this because you can, the thing is, if you have something which is Lipschitz, so you apply a Lipschitz function to a Hölder continuous function, then the composition of these two is again, this has the same Hölder regularity. You can also apply a Hölder function to a Hölder function, and then you get something less. Yeah. So you can, not Lipschitz, so you can have something weaker. And you can weaken this assumption here, twice continuous differentiable, by using that and still make sense of the integral. Okay, to make sense of the integral, there are two Hölder exponents that have to sum up to 1. And this is where you can weaken these assumptions, I think. But I think here, twice should be enough, because in the rough path space, you have 3. And this is also enough. In the Young case, 2 should be enough as well. Fair enough. You can prove me wrong if you have, but I think here it should be safe.
More questions? Okay, so then thanks again, Sebastian. So we have now our coffee break, and I just want to make one announcement for the foreigners, so for the non-Brazilians. Please go to the registration desk, because there will now be the payment of the per diem. Yeah? So this is for the foreigners, for the non-Brazilians. Okay, so see you at 4.
About the flow properties, but in the usual stochastic differential equation, you use Komogorov equation to prove continuity.
Of course. I mean, you can, but I just want to say that there is an issue you have to solve. I mean, if you just use the Ito
take my mask off so we can hear you better? Yeah.
So that's,
So, welcome everybody to the last session of today. So we will have 2 short talks, and the first one is going to be given by Beatriz Salvador from Lisbon. And she's going to talk about the gradient version of the generalized symmetric simple solution.
Okay, so good afternoon. Today I would like to talk a bit about a model that was introduced to me during my master's degree. So it is an interacting particle system, meaning that it is a continuous time Markov chain with finite state space, for which we prescribe dynamics that is a superposition of essentially 2 dynamics. One coming from the bulk, so the points from 1 to n-1, and also a boundary interaction, which are going to be given by the interaction between this left reservoir with the point 1 and the right reservoir with the point n-1. So we're going to have particles that interact with each other with a certain rule and the jump rate, which are given here. And the model is said to have an exclusion rule, meaning that we do not allow more than alpha particles per side. Probably many of you are familiar with the classical exclusion process, meaning that we have only 1 particle per side. So for the generalization we are doing here, it's that instead of just 1 particle per side, we'll allow at most alpha. It is said to be simple because the interaction between particles will be to nearest neighbors, meaning that they can only jump to, so a particle, if it is at point x, jumps to x plus 1 or x minus 1. And it is symmetric because it has no preference way to go, either left or right. The boundary interaction is tuned by a parameter theta, so the strength of this interaction that, as you will see during the lecture, it will play an important role on the boundary conditions that we will obtain for hydrodynamics and also for fluctuations. That is what I want to talk a bit about today. So, to properly define our theoretical particle system, we have a state space omega n, which will be the state of configurations. And we describe the dynamics by its Markov generator, which is, as I said, the superposition of the dynamics coming from the bulk and from the 2 boundaries. As you saw on the name of my talk, I was going to talk about a gradient model. By gradient, I mean a model for which the action of the generator on a single side can be written in terms of a double gradient in some sense. So what I mean is that the current of our system, it will be also of gradient form. So why this is important is because when we are trying to prove hydrodynamics, it will allow us to perform integrations by parts twice. So essentially all the derivatives in some sense that will appear at the side of the process will go to the test function. This process was also introduced in the Kimble-Islandine book with a different choice of rates for which this model is non-gradient, which are these ones here. But I will not focus on those, but rather on the ones that I presented first. But it's just to show you that the choice of rates that you do for your process, even though they both satisfy this exclusion rule, it will determine if your model is gradient or not. I would like to first start by making a parallel between hydrodynamics and fluctuations. My motivation is because when I started working with this model, it was on the stochastic duality side, which I will also talk a bit about. We will need it. And And then I studied the hydrodynamic limit, and from that, fluctuations, which is more or less the typical thing to do after we prove hydrodynamics. At the level of hydrodynamics, essentially what we want to prove is some sort of law of large numbers, while at the level of fluctuations, what we want is a central limit theorem. So at the hydrodynamic limit, we start by defining the empirical measure that you can see here in this formula. And from this one, we define trajectories of measures given by this formula here. Okay, so testing against a test function. At the level of fluctuations, we have something which is very similar, but now we are on the scale of the central limit theorem, and we define the density fluctuations field. From both these two definitions, we can define a sequence of probability measures, the QNs and these other QNs that are slightly written different, but more or less they have the same aspect. The only thing that's changed is the field. So here we have the fluctuation field. Here we have the empirical measure, so that in terms of trajectories. And in both cases, what we want to prove is a weak convergence of this probability sequence of probability measures. While on the hydrodynamic limit, what we can prove is a weak convergence that it will be the limit point uniquely characterized by being concentrated on a unique trajectory that it is a measure which is absolutely continuous with respect to Lebesgue. While at the level of fluctuations, what we can prove is that up to a subsequence, our limiting point, it will be, so we have convergence, and the limiting point are probability measures that are concentrated on paths that decompose in this formula here. While at the level of hydrodynamics, the uniqueness is something that we get for free from the uniqueness of the solution of the hydrodynamic equation. At the level of fluctuations, this is harder to prove because we need to have some assumptions on the initial time in order to have uniqueness of the limiting point. So in order to have that, it is not up to a subsequence that we have the convergence, the weak convergence, but to the whole sequence that it is uniquely characterized. We need to have these assumptions here. What is the strategy of proof for both? So we have at the hydrodynamic, since we have a gradient model, we can apply the entropy method, which is described in the Kimbley-Landin book. You can find it on chapters 4 and 5 for those who are interested. And at the level of fluctuations, this is also described in the same book. It's probably the famous one and the main textbook in chapter 11. In both cases, you always need to prove tightness of the sequence of measures and characterize limit points. And what I want to focus from this point on is on the proof of fluctuations, the tightness part, we need to have control of the time-dependent correlations functions. This is something that it is done for the case alpha equal to 1, so for the classical exclusion process, but for this one, since it is non-integrable, we do not have that much information. So this was the novelty that I wanted to present to you today. So we are interested in finding good bounds for these correlations functions that what allow us to prove the tightness of the sequence of measures for the measures which were induced by the density fluctuations field. So let us first look as motivation for the case alpha equal to 1. So if we write down the Chapman-Komogorov equations for the correlations, what we find out is this formula here, where this A theta n is a Markov generator of a two-dimensional random walk on the triangular that have a jump rate everywhere 1, and it gets killed when it goes to the boundary at weight 1 over n to the theta. And the remaining term here that is not written in, is not a function of the correlation, is a function that only lives on this main diagonal. So if we get inspired on this, which we can solve it by using the Feynman-Cox formula, we want to find a similar equation for the correlations for the generalized exclusion. But what is the problem is that if you try to write down the Kokomarov's equations, it seems that there are no nice way to write down as a formula from the case of a similar for the case alpha equal to 1. So I was having a meeting with my supervisors from the masters, Patricia and Chiara, and we were struggling with this question of how to change this function in order to get the system of equations to be nicer. And at some point, Chiara told us maybe we should look at the duality function. And so this is where duality comes into place. So what is stochastic duality? So we have two processes, and we want to connect them by a function d called the duality function that satisfy this relation here. So you can interpret it in the following way. What you expect when you let time evolve on the first process by the means of this duality function should be the same as letting time evolve, but on the dual process. The duality function and the dual process, they are not unique. It is easy to see that if you multiply the duality function by a constant, of course, this equality still holds. And when we have two processes, a process that it is satisfy this relation with itself, we say that it is self-dual. In our case, our process with the boundaries is not self-dual, but it's almost. So the price we have to pay to add the boundaries is that instead of having a dynamics that we can have injection and remove particles, on the dual process, this is simplified by having dynamics that only observe particles. So it was proven in 2013 by Carinci, Giardina, Ghiberti, and Redig that with this duality function, our process is dual to essentially the same dynamics on the bulk, but now replacing the boundary by dynamics by only observing boundaries. And you see, since this duality function here, okay, this duality function here is of product form, we're gonna do a clever choice of the configuration on the dual process in order to use the duality property, so this expression here, to get some information in terms of correlations. And the thing to do is the following. So we choose at the level of the dual process the configuration where we replace a particle at site x and a particle at site y. Then the duality function is very simple. It's something that is very related to the correlations. And so this is what motivated Chiara to tell us maybe we should look at the duality function. And she was right. Because if we construct this function here, the GT, this is exactly the function that corrects the terms from the Chapman-Komarov's equation of the correlations that were not good. You see that here we have a dissonant centralization that it should be like the simpler thing to do. So this was a trick. And the idea is that when we are on the main diagonal, if we choose a sequence of measures which are homogeneous product measures of marginals binomial distribution, then this GT function vanish. So now as you see, as I was saying, the GT is exactly a generalization of what we get for alpha equal to 1. And from here, our life is much easier than it was before. So we can use the Duhamel's formula or Feynman-Cox as you want, do some bounds and find that in order to have bounds on the correlation function, the time dependent, all we need to do essentially is have a certain assumption on what happens on the G function at time 0, so that it's maximum, and try to find a good bound for this occupation time. This occupation time, if we write down the Komogorov equations, you find this system here that for t equal to 0, for Liggett's conditions and our model, meaning that we choose the parameters on the boundary in a certain way related to alpha, we can find an explicit expression for it, which gives us that if x is different from 1 and y is different from n minus 1, then its order of decay is of order 1 over n, and otherwise it is 1 over n squared. So with this, what we did was the following. So we could not get an explicit expression for the time occupation when theta was different from 0. And so the idea was to try to compare the occupation time with theta equal to 0. With theta and the theta equal to 0. And to do that, what we did, and this is the contribution I think we gave to science, it was to construct this t function that essentially is the difference of the occupation time with theta with minus the occupation time with theta equal to 0, plus an extra term that is essentially a constant, except when so it's essentially a constant everywhere, but it changes, so it's vanished when we are at the boundaries. And making this artificial adding of this constant here that will depend on theta, that will not give you that much details because it's something that we are still working on. So this is really fresh work. We can get, instead of a system of equations with equality, we get an inequality. And with this, we can apply a maximum principle to say that the occupation time with theta is bounded by the occupation time with theta equal to 0 minus this mysterious constant here. And with this, we could improve the bound for the occupation time with theta, that it is now of this order. So we can use what we knew for the case theta equal to 0 and get back to our computations for the bound for the correlation function and obtain the following result. I just wanted to say that these bounds is one of the building blocks to prove fluctuations, because the tightness part depends on the knowing such bounds. Okay, so okay, so let me now just ask for your attention for this term here. So this bound, it becomes bad, so in the sense that it doesn't give us good information in terms of decay with n when theta is bigger than 2. Because this term here, it will become something of the order which is greater than 1 over n. And this is not good. So in order to have a better bound for theta bigger than 2, we need to work a bit more. But what we did was essentially follow the same strategy that it was already done for the case alpha equal to 1, that you can read on the paper of Milton, Otávio, Patricia, and help me please, and Adriana, right? And Adriana, exactly. So it's essentially the same strategy of proof. Instead of writing the Markov generator that we had before for the equation for the GT, we compare the Markov generator of a two-dimensional random walk that it is reflected on the boundary. So we take the boundary terms to be encoded on this b theta n, that it is always negative. And it is the fact that it is negative that in some sense we will just throw it out, because we can bound it in in a very nice way. So we can do the same type of tricks we did before. So use the Feynman-Cox formula, bound the term with the for time t equal to 0. And the remaining terms, we can just do the same kind of tricks. The only difference is that now the occupation time will be a function of t. We will not bound it by taking time to infinity, because the strategy of proof, the bound for this term here, asks for this t. Okay, so if you want to see more of this, you can find it in the article that I already mentioned it. So this is what we have been doing in the past 1 year, more or less. So the first part, it was hydrodynamics, and now fluctuations. So we want to be able to also obtain the same similar bounds, but now taking the initial measure to be the stationary measure, which is something that we still don't know how to do it. And from these bounds on the stationary correlation functions, try to prove a hydrostatic limit, which is already done for alpha equal to 1, and go to large deviations, which I hope it will be my PhD. So thank you very much.
So, is there any question from the audience? Yes?
So you said you have to look at the function g at time 0, right? And also on the correlations. So my question is, if you assume anything in the initial measures.
So what we assume in terms of the g is that at time 0, it has to have this decay here. Okay, and if you start by a measure which is the product of binomials, this everything works, because the GT will be essentially 0. So yeah, you have an example of a sequence of measures for these where these assumptions hold.
Okay, so any other question? Well, if not, let's thank the speaker again. So let's take a minute to prepare for the next talk, maybe. Okay, so our next speaker is Chuchen Chu from Salvador. He's going to talk about the scaling limits of local functions in one-dimensional exclusion process out of equilibrium.
Okay. Thank you very much. I would like to thank the organizer for giving me this opportunity to present my work here. It's a pleasure to me. So is that okay that I leave this I leave my slide in this way, not for full screen? Okay. So today I will talk about the scaling limit of local functions in one-dimensional exclusion process out of equilibrium. So. Thanks. So the plan of my talk is as follows. So first, I will tell you what is additive functionals of extrusion process, and this is the object that we would like to study. And then I will tell you the previous result on the scaling limit of additive functions of extrusion process. But all these results are about the process starting from equilibrium. Then in the end, I will talk about my result, which is the limit when the process starts from non-equilibrium. So let me first introduce you the extrusion process with finite range jumps. So the extrusion process, so we consider the one dimension. So the extrusion process is a Markov process defined on some lattice S, and S could be the discrete torus or Z or ZD, and for each side, we at most one particle is allowed. So we use at x equal to 0 represents that site x is empty, and at x equal to 1 represents the site is occupied. So now let me tell you the dynamics. So you fix, you associate to each site x to a value, a non-negative value lambda x, and let's call it by holding rate, and you fix a probability measure p. So the dynamic is the follows: if the site x is occupied, then the particle stays at site x for exponential time with the intensity lambda x. Then it tries to jump to site y with probability p of y minus x. So if site y is already occupied, then the jump is denied, and then you wait another exponential time of lambda x. So I will call the product of lambda x p of y minus x as the jump rate, and we denote it by rxy. So we can also, so the generator of this extrusion process can be given in this way. Okay. So now let me tell you what is the local function. A local function is a function which depends only on finite many sites. And these are some examples of local functions. What we are going, we would like to investigate the following kind of object. So this is a simple example. So the integral from 0 to t of eta s of x of ds. So this represents from time 0 to t, how long does site x is occupied. So that's why we call it occupation time at site x. But we can consider a more general object, which is given a local function, we would like to study the long time behavior of the integral of f eta s. So there are two types of questions that we can consider. The first one is easier. So we would like to find where can I see? We would like to find Vs such that the integral of this function f minus Vs, then you divide by t. When t is large, this goes to 0. So this is some sort of a law of large number. Once you have the law of large number, you can consider the central limit theory. The central limit theory is as follows. You would like to change here, change to t from change t to some smaller value, which is t to the alpha, and you want to find a proper alpha such that this quantity converts to something reasonable. Now let me tell you the previous results. So all the previous results, since my work is on the one-dimensional extrusion process, I also only mentioned the previous result only on one dimension, in that one dimension. So you consider a finite range finite range extrusion process on Z, meaning that P, the probability P has a finite support. And you assume that the holding rate at each site is the same. So for this dynamics, you can easily get that the invariant measure of this process is a Bernoulli product measure. So we assume that the process starts from its invariant measure. So the first result is from Saturama, Shu, and then Satulama. They assume that the mean of P, they assume that the probability P has mean 0. Then they prove that this process, which is so they speed up the process by n square, and then they center the occupation at site 0, the integral over time, then they multiply a square root of n. They prove that this process converges to a fractional Brownian motion with the Hurst exponent 3/4. Then later on, this result was extended to local functions. So given a local function, you define phi f as the expectation of f under the probability mu rho, where mu rho is the invariant measure. Gonsalves and Jara, Milton Jara, proved that this process where we replace the occupation by this more general object, this process converges to a 3/4 Brownian motion times some constant, where this constant is you take the time derivative over rho. So let me tell you an example. Let me use an example to explain the previous result. So if you take a local function f as the product of eta 0, eta 1, eta 2. So by the previous definition of phi rho, you can see that phi rho, you can compute phi rho and the phi prime rho. So the result tells you that this quantity converges to this guy. Okay. In the same paper of Gonsalves and Jara, they prove the similar result for the weakly asymmetric extrusion process, where the strength of the asymmetry is of order 1/n. So now the limit process is no longer a fractional Brownian motion; it is a Gaussian process. Okay. Now let me tell you the model that we work on. So we fix a smooth function on defined on the continuous torus, and we consider the extrusion process defined on the finite torus with n sides in this way. So at each site, x, the particle can jump to one of its neighbors with the rate 1, jump to the right with the rate 1 plus 1/n times f of x divided by n. And to the left with 1 minus this guy. So this model was has the following feature. So you cannot so the Bernoulli product measure mu rho is not the invariant measure. You don't know the explicit formula of this invariant measure. So all the previous method from Gonçalves and Jara's paper will not work for even for the equilibrium case. So when f equal to 0, this process becomes the symmetric simple exclusion process. Now I want to tell you some results from a paper of Jara and Meneses. So given a smooth function, you define a Bernoulli product measure associated to this profile rho. And let me recall the relative entropy of two measures. It's defined in this formula. So so let me donate by the distribution of the speeded up the process at time t is donated by nu tn. So in work of Jara and Meneses, we prove that if the initial relative entropy is of order big O1, then at any time, finite time, the relative entropy is of order big O1, where this reference measure is associated to some profile, and this profile is the solution of this following PDE. With the previous entropy bound, you can easily derive the hydrodynamic limit equation. Once you have the hydrodynamic limit equation, you can start to consider the fluctuation. So the fluctuation field is defined as follows. Let's call this fluctuation field as xn. So what they prove in the paper is that this xtn converts to some xt, where xt is the solution of some stochastic PDE. They give the meaning of this solution in terms of martingale. Okay. So now let me tell you our result. So we start with some function phi, which is smooth with support on 0, 1 and has integral 1. And we define the multifilar of this function phi u. This phi epsilon can be think as the smooth version of this renormalized indicator function on the interval from 0 to epsilon. Then given a smooth function q, which is bounded away from 0 and some epsilon, we define the following process. Recall that this xs is the limit of the density fluctuation field. So this part inside this big brace is kind of complicated, but it will be clear later why we choose these guys. Okay, so our first theorem said that this d epsilon qt has some limit, and when epsilon goes to 0, and we call it as zqt. Okay. So now we would like to define the object that we would like to study. So we fix a finite set B, and for each non-empty set B, we define the following object. So here is the centered occupation at site X. Then we take the product, then we divide by QS for at time S. Then we take the integral, then we times the square root of n. So what we can prove is that when B has only one side, the limit of this guy converges to zqt, where zqt is the limit that appears in the previous result. Okay, maybe I skipped it. So our next result is that when B has more than 2 sides, the previous object that we defined convert to 0. So let me try to convince you why the limit is 0. So you define this wy in this way, and with this notation, you can write the gamma nb in the following way. So let's take an example when B has only 3 sides, -1, 0, and 1. Okay. Then you can do some replacement lemma, and you replace W1 by this W1 where with some error. This is the average of size of W1 plus Z, where Z is from 1 to epsilon. And you can also replace this W minus 1 by this guy. This W epsilon 1 and W epsilon n minus 1 are very close to 0, and they are sub-Gaussian variable of order this guy, 1 over epsilon divided by n. And with this, you can conclude that this tau n bt convert to 0. Okay, so now let me tell you the final result. So suppose you are given a local function, and like before, you define phi f rho as the expectation of f under the Bernoulli product nu rho. So our theorem said that if you first center this guy, if you first center f eta, then divide by 1 of bs, this limit, the limit of this guy is z of b divided by phi prime of rho t. This quantity is already defined in our first theorem. So how to prove this theorem? I will give you an example. Suppose f is depends only 2 sides. F is equal to eta 0 and eta 1. So the phi prime is equal to 2 times rho s0. Then you write this guy, namely this guy, in this form. So the first one is the sum of two things, but each the first one can be the so the first guy can be the limit of the first guy. We can use our first theorem, this theorem, when B has only 1 side, and we have the limit ZQT. And the second guy, we can use our second theorem for when B has more than 2 sides and the limit is 0. So only the first part contributes. So the limit, you can see the limit is this guy, which is this. Okay, this is the reference. Thank you.
So, do we have any questions from the audience? Yeah.
So I have a question about the theorem where B has more than 1 side.
Yes.
So, yeah. So this kind of shows you that multiplying by square root of n is probably not the right thing to do.
Yes, you have to find a better, a larger.
Exactly. Do you have any conjectures? Something like square root of n to the cardinality of B?
Yes. So I think there's a conjecture. It's like follows. So here has to be, I think, is to be n times log, right? Okay. I mean, if you want to write in this way, it has to be n divided by log square.
And it's a conjecture for 3 sides?
3 sides,
Yeah,
I
3
think
sides.
it's, I'm not so sure. I think it's this. It's correct of me. Yeah. Okay.
Well, okay, thanks.
Okay, so any other question? Okay, so let me, maybe I could make a question. So I was puzzled about your function 1 over q, and then I realized that a very nice 1 over q function that you can take is actually the standard deviation of your function f.
The what?
The standard deviation of your function f. And so do you just for did you do the computations for that particular function to see if your process z the qt is nicer in that case or in some way, or is computable or something like that?
I'm afraid not. It will be very complicated when I compute the covariance.
Okay.
Even for the simple exclusion process, simple symmetric exclusion process.
Okay. Well, if there are no more questions, let's thank Chuchen again. And maybe a quick announcement. Let me see. Yeah. So to remind you that dinner is at 6:30, no? Yeah. So remember that dinner is at 6:30, so you have to be there at 6:30, otherwise you will lose dinner.